In this video, we're going to illustrate the Catkin workspace that is provided for you for Workshop 8. And we will discuss some elements of software architecture as we go along. We will be using ROS. Some of the packages we will be using would be something like an event wrapper. Notice that we're using the word wrapper because it's a pattern. And what we're doing here is converting a callback procedure, in a sense a subscriber pattern, into a server pattern. The first thing we're going to do here is compile. And in here, I'm going to run it. After compiling, that wrapper is in the developed in its own folder. So we're going to run it. And I'm going to run raw score, which is the mid. And as you can see, we get an error. We run raw score. Fire this node. It's a subscriber and it's a server. So once I have it run it, you can do something like ROS topic info. So let's start with ROS topic list. So you'll get to see that this guy is running. Somebody can publish here. And let's get some information about it. I don't expect you to be a ROS expert, but you can see here that there's somebody subscribed to it, and this is particularly this guy. So we can actually publish events. This will enable us, for example, to open the door or to close the door. And we have somebody who registers that the door is closed, or we can issue a toast to start the toaster, or we can issue a bake to start. And in particular, also what I can do is to look at the service that this provides. So similarly, ROS service, who's there? And there are two services. What door event has been recorded? So let's get ROS service information about, for example, whether a functionality has happened. The node is the event wrapper and doesn't need arguments, so we actually can just call it. And at the moment it tells us that, yeah, there's been an event for toasting, an event for baking. The interesting thing is this thing, once it consumes the event, it makes it false. If we put, again, for example, bake, then we can query to a server, has bake happened? And it says yes, and because it answered us already, it consumed the event, so the next time is false. The same thing if we call the other service that we have here, whether the door has been opened or not. Because we had messages here, events, it says yes, those events have been recorded, but if I call it again, now they've been erased. That's part of the functionality of the module that's running down here. Let's open the door. That event gets recorded. So if we ask, has the door been opened? It tells us yes. Has there been another event since? No, we have consumed the event. There's a little tester node here which consumes the events. For example, say open. The tester here checks that the event has been received. So this is now a consumer of the events, polling for events, and can say, oh, close has been received. The same for toast. So this is a way to check that we can read programmatically the different events that we post here. For example, post toast. This guy tells us it has received it. So this illustrates that this package here works as a recorder for events, and it can have a client who can poll when the event has happened. So now we're going to illustrate the first behavior, the inner machine. Go into the package that is here, and we're going to set it up. We're going to set it up because otherwise, if you go inside del lib, although the machine has been compiled, we don't have a path for the scheduler of logic label finite state machines to operate on. In here, you should have the script machine set up, and we just call the machine. We have the inner machine. So now what we do is copy the compile machine into the area where the scheduler expects it to go. Similar as before, we're going to run raw score. And in a sense, we have to turn on the sensor. So we run again this guy, who is our event wrapper. And now using CLFSM, I'm going to run first the inner machine without details of the state. So the machine starts with the arm time event. We can send the toast message. The toast message doesn't do anything while we're already toasting, but if I send a bake message, we have an action because we leave the toasting state, and we have an action because we enter the baking state. So if I send bake again, this has no effect, but if I send toast, the on exit of baking, which is to set the temperature to 0, happens, and then the arm time event, so we are toasting for a certain amount of time. If I toast, that has no effect. Let's bake. It changes to the state of baking. If we toast, it goes back to toast. Even if you type Ctrl+C here, it may be the machine does not stop because we have not put everything about raw score. But if you find the process, then you can kill it this way by its process number. And just for completeness here, I'm going to run it in verbose mode so you see all what's happening inside the machine. So you can see the machine is polling for the event. Because it's toasting, let's bake. You're going to see the bake output come, and now we are in the machine checking if we need to transition the state. Toast again. You saw briefly the toast message go by. Another toast message has no effect, as we just already saw, but a bake message does move the machine forward. Now let's do our PS command again. Find the process of the machine, 21006. Raw score, don't let it go running forever, kill it occasionally. It's a very heavy process. There is a second machine called Outer. Although it's already compiled, we don't have the path for the scheduler. So we're going to do the same as before. Go into Outer machine, and we're going to run the setup script with Outer. Don't worry too much about this. This is just a technicality so that you see that in the bell lib, now we have a path for it. Copy the Outer machine into its path for the scheduler, which requires here to remove the little prefix lib. And we're in a position to run the Outer machine. Now, remember, we need to turn on the sensors, but we need to turn on the middleware to enable the client service pattern to be enacted. No message has been received about the door, so let's close the door. That's going to have no effect. But if we open the door, the heater is off and the lamp is on. If we send another message that the door is open, nothing happens until we close the door. The heater becomes on. Let's open the door and close the door one more time. Let's kill the execution of the machines, and I'm going to run it now in verbose mode. Let's open, and you see something has gone through. Let's close, and something goes through. Let's kill it again. And now what I'm going to do is run it simultaneously. And here is where I expect you to observe the behaviors close the door, what do you see happening? What happens if we open the door? What happens if while we open the door, I say toast? Nothing should happen because the door is open. What happens if I say bake? Again, nothing happens because the door is open. What happens if I say close? The door gets closed and we are in baking because the event got recorded. So let's do toast. And now we change to toasting with the door closed. Let's bake. We change to baking because the door is closed. Let's toast again. Bake. While baking, let's open the door. What happens if we close the door? We are by default in toasting. Now we're baking because the door is closed. Toast. This seems to work, but there's some anomalies. It is part of the exercise for you to discover such anomalies.